Have you ever looked at a massive bridge or a skyscraper and just wondered what is really holding all of that together? Well, it's not just the steel and concrete that you can see. Deep inside, there's this whole invisible network of forces constantly pushing and pulling. So today, we're going to go inside the material itself and uncover what those hidden forces are all about.
Take a look at something like a dam or a retaining wall. These things have to fight against colossal pressures from soil and water every single second. They aren't just sitting there. They are these incredibly dynamic systems where huge forces are always at play deep within the structure.
And that leads us to the really big questions, right? What exactly are these internal forces? How do they even work? And, maybe most importantly, if we want to build things that last, how do we find that one single weak spot, the exact point where failure is most likely to start?
So, here's our game plan. We're going to start with what stress actually is, then look at its two different faces. Then we'll see why your perspective on it changes everything. After that, we'll find the secret to simplifying it all, connect it to how things physically bend and stretch, and finally see how engineers use this knowledge to design everything around us.
Okay, first things first. Let's get a handle on what's happening inside any material that's got some kind of load on it.
So in engineering, we call this internal pushback stress. You'll see it written as the Greek letter sigma. But really, you can just think of it as how a material fights back against an outside force. It's not just about the force itself, but how that force gets spread out. A tiny push on a needle point can create way more stress than a huge push spread over your whole hand. Now, here's the thing about stress. It isn't just one simple concept. It kind of has two totally different personalities that describe how it behaves. The first one is called normal stress. This is the one we're probably all familiar with. It's a straight-up push or pull on a surface. But the second one, shear stress, or tau, that one's different. It acts parallel to the surface. Think about sliding a book across a table, or how scissors cut paper. That's a shearing force.
And this is where it all comes together. If we could zoom in, way down to a single point inside that dam, we'd find a tiny little cube of material just like this. And it's getting pulled and squished by normal stresses while also being twisted by shear stresses all at the same time. It's this really complex, messy situation.
Okay, but this is where it gets really, really interesting and a little weird. The amount of stress you actually measure, it completely depends on your point of view.
Yeah, seriously. Imagine you slice through that tiny cube. If you cut it straight on, you'll measure one set of normal and shear forces, but if you slice it at an angle, you get a completely different set of numbers. The forces inside are the same, but what you measure changes depending on the angle of your slice.
And you can see how this would be a huge headache for an engineer, right? If the stress values are different for every possible angle you could pick, which one do you actually use? Which direction reveals the absolute maximum stress, the one that's going to cause the whole thing to break?
Well, this brings us to the solution. And it's this really beautiful, elegant idea that just cuts through all that complexity. It's called the principal direction.
And this simple statement is the whole key. It turns out that no matter how complicated the forces are, there's always a special angle, a perfect orientation, where all that messy shear stress just completely vanishes. And we call those special angles the principal planes.
And here is the aha moment. When we line up our viewpoint with these principal planes, the only stress left is pure normal stress, just a direct push or a direct pull. These are the principal stresses, and they are the absolute maximum and minimum pull or push that point is feeling. This is the number we've been searching for.
This visual just makes it so clear. Look at the left. That's our original complicated mess with both normal and shear stresses. But if we just rotate our perspective by that special principal angle, theta p, look what happens on the right. Bam, the shear is gone. All that's left are the principal stresses, sigma 1 and sigma 2. We found them. We found the true maximums.
And you know what the best part is? We don't have to go searching and checking every single angle to find this magic orientation. Thanks to some clever math, engineers have a powerful formula that just calculates it directly. And here it is. Now, I know this equation looks a bit scary, but just think of it like a recipe. We don't need to get bogged down in solving it. What's important is that an engineer can take the stresses they measure in any direction, the sigmas and the tau, plug them into this formula, and out pops the two numbers that matter most, the absolute maximum and minimum stress. It's the key that unlocks the whole problem.
So, now we understand these invisible internal forces, these stresses. Let's link them to something we can actually see and measure on the outside. How the material physically changes shape.
It's a really straightforward cause and effect relationship. Stress is the cause, it's that internal force. The effect is what we call strain, represented by epsilon. And strain is just a fancy word for how much an object stretches or squishes or deforms because of the stress it's under.
Of course, not every material reacts the same way. A rubber band and a steel bar are going to behave very differently. That relationship between stress and strain is defined by a material's unique properties. Things like Young's modulus, which tells you how stiff it is, or shear modulus, which describes how much it resists twisting. This is literally why rubber stretches so much more than steel under the exact same amount of stress.
All right, let's pull all of this together now and see why finding that maximum principal stress is, without a doubt, the most important step in real-world engineering.
And this is really the bottom line. An engineer can't just look at the weight sitting on a beam and call it a day. They have to use these ideas to look deep inside the material, find that hidden principal direction, calculate that maximum principal stress, and then make sure the material they chose can handle that specific value. That is the true test of the design.
And hey, as a little bonus, once you know those principal stresses, you can instantly find the maximum shear stress too. And for certain materials, especially metals like steel that can bend a lot before they break, this maximum shearing force is often what actually causes them to fail. And as you can see, that simple formula ties it directly back to our principal stresses.
So the next time you drive over a bridge or walk past a skyscraper, think about this. You're not just looking at steel and concrete anymore. You're looking at a masterpiece of engineering, a physical solution to this incredibly complex puzzle of hidden forces, all designed to withstand that one single value that matters most, the maximum principal stress.